this video, I will talk about the concept of exponential functions. To understand what an exponential function is, let's take a look at this case. Suppose there is a number, the value is 1. If you multiply 2 to this number, you will get 2. If you multiply 2 to this number further, you will get 4. And if you further multiply this by 2, you will get 8. And then 16, and then 32, so on and so forth. In mathematics, we describe that this number actually increases exponentially because each time this number has been increased by same factor as before. So in mathematics, this kind of increasing trend is known as an exponential growth. And since each number has been increased by 2 times as the previous one, this is known as the exponential growth with a growth factor which is equal to 2. And this increasing trend can actually be represented by this function, 2 to the power x. Because 1 can be represented as 2 to the power 0. 2 can be represented as 2 to the power 1, 4 is 2 to the power 2, 8 is 2 to the power 3, 16, 2 to the power 4, and then 32 is 2 to the power 5. So if we input 1 into this value x, then we will get 2 here. If we input 2 here, then we will get 4. If we input 3 here, then we will get 8. If we input 4 here, then we will get 16, so on and so forth. So this function can actually represent this exponential growth here. So in mathematics, we call this function an exponential function with base 2. Base is the number that we need to raise a power to it, and in this case, this is 2. So when you have a function with a constant base, and x as the power, or what we call the exponent, then this one is known as an exponential function. So here we have an exponential function with base 2. Now let's take a look at another case. Suppose now this number 1, instead of multiplying this by 2, we multiply this by half. And then we will obtain half here. And if we further multiply this by half, then we will obtain a smaller and smaller number, so on and so forth. And as you can see, in this case, this number is not increasing. Instead, it gets smaller and smaller. And each time, this number is calculated by multiplying the same factor than to the previous one. So this case is known as an exponential decay. Instead of a growth, if we multiply a number which is less than 1 each time, then it will result in a decay instead of a growth. So in this case, we will say that the decay factor of this exponential decay is equal to half, because each time a new number is produced by multiplying half to the previous number. And similar to the previous example, this exponential decay can also be represented by a function like this, half to the power x. Because 1 can be understood as half to the power 0, half is half to the power 1, 1/4 is half to the power 2, 1/8 is half to the power 3, this one is half to the power 4, half to the power 5. So as you can see, if we input 1 into x, then we can get this number. If we input 2, then we can get this number. 3, this number. 4, this number. 5, this number. So this one is also a function that can describe this exponential decay. And we call this also an exponential function. And this time, this one is an exponential function with base half. And now let's compare these two cases and try to come up with some conclusions. So as we can see, for an exponential function if we have a base which is greater than 1. And that's what we have in this case. In this example, the base is 2, which is greater than 1. And if the base is greater than 1, then when we multiply this base to the number, then it will increase exponentially. So if the base is greater than 1, then it will result in an exponential growth. That means we will get an increasing exponential function if the base is bigger than 1. On the other hand, if the base is less than 1 and greater than 0, and of course, the base here should be positive. If this number is negative, then this one is not similar to this case. So if the base is between 1 and 0, and that's what we have in the second case, it is half. So if the base is smaller than 1, then when we multiply this number each time, the number will get smaller and smaller. So instead of a growth, here we obtain a decay. And that means the exponential function here should be decreasing. Decreasing means if the value of x increases like this, 1, 2, 3, 4, 5, if the value of x increases, the value of this function actually decreases in this way. The number here just gets smaller and smaller. So to conclude, if the base is bigger than 1, then this is an increasing exponential function. And if the base is less than 1, then this exponential function is decreasing. Now let's take a look at how the graphs of the exponential functions look like. From the previous discussions, we know that an exponential function is a function in the form of this, a to the power x. A is the base of these exponential functions. We already know that if the base is greater than 1, then we will have an exponential growth. That means this function is increasing. And if a is between 1 and 0, then we will have an exponential decay. That means this function is decreasing. Then we can take a look at how the graphs of this exponential function look like on an xy plane. So we need to consider this equation and see how the graphs will look like on an xy plane. So let's consider this. We need to separate this into two cases. First of all, we need to consider the case in which the base is greater than 1. So for example, 2. So let's see, if x is equal to 0, then y will be 2 to the power 0, which is equal to 1. And if x is 1, then y will be 2. If x is 2, then y will be 4. If x is 3, then y will be 8, so on and so forth. But here x can be negative, as negative indices are defined. So when x is minus 1, then the value of y will be half. If x is minus 2, then the value of y will be 1/4. If x is minus 3, then it will be 1/8. So when x is positive, then you can see that the value of y is actually increasing. And towards the negative side, if x is negative, then you will see that the number will get smaller and smaller, closer and closer to 0. So the graph will look like this. It will pass through 0, 1 here, as a to the power 0 is equal to 1. Then towards the positive side, the number will increase, the value of y will increase. But towards the negative side, the number will get smaller and smaller, closer and closer to 0. And this will never touch the x-axis. It will just get closer and closer to the x-axis, but never touch it or cross it. So when the base is greater than 1, we will result in an increasing function like this. Towards the positive side, the value of y is increasing, and towards the negative end, the number is closer and closer to 0. And for the other case, when the base is smaller than 1 and bigger than 0, so for example, we consider half in this case. So when x is 0, the value of y is 1. And if x is 1, then the value of y is half. If x is 2, then it will be 1/4. If it is 3, then the value of y will be 1/8. So that's the positive side. And similar to this case, x can be negative. And if x is -1, then the value of y will actually be 2. If x is -2, then the value of y will be 4. If x is -3, then the value of y will be 8. Now we can see the trend here. So in this case, the graph will look like this. Again, it will pass through 0, 1, as a to the power 0 is still 1. Now towards the positive side, the number will decrease. It will get smaller and smaller, closer and closer to 0. That means it will get closer and closer to the x-axis. But towards the negative side, the value of y will increase rapidly, like this. So when the base is smaller than 1 and bigger than 0, then you will have a decreasing graph like this. And if you compare these two graphs, then you can discover that if you flip this graph horizontally, if you flip this graph horizontally, then you will actually result in this graph. So if you flip this, then you will get this one. So these two graphs are closely related to each other. So to conclude, for an exponential function y equals a to the power x, if a is bigger than 1, then we will have an increasing graph with the y-intercept which is 1. And if a is smaller than 1 and bigger than 0, then we will have a decreasing function. But same as this case, the y-intercept is still 1. So we will have a decreasing function like this. So in both cases, the graph will never touch or cross the x-axis. It will just get closer and closer to the x-axis. And on the other side, it will increase very rapidly, like this. So these two graphs actually look very similar to each other. Now let's take a look at a concrete illustration of how this value of base can affect the shape of this graph. Here we have an exponential function with base 2, an increasing function. If the value of this base increases, then you can see the graph will get steeper and steeper. It will increase more rapidly. And if the value of this base decreases, then it will increase less rapidly. And particularly when the base is equal to 1, like this. Then this one is not an exponential function. This is just a constant function because 1 to the power x is always equal to 1. And if the number decreases further, if it becomes less than 1, then it will become an exponential decay, a decreasing function. And if this number decreases, then the graph will decrease more rapidly. So that's how the value of the base can affect the shape of the graph. Now let's take a look at this example. Suppose now I have a graph of this exponential function with base 3. Now I want to sketch these two graphs on the same xy plane here. Let's see how we can do this question. Suppose now I want to sketch y equals 2 to the power x. You may need to consider a horizontal line like this. This is y equals 1 to the power x. This is not an exponential function, just a horizontal line. But you can use this line to help you to sketch this graph. So compared to base 3, base 2 is closer to 1. than base 3. So that means this exponential function should be closer to this horizontal line when compared to this exponential function. So this exponential function is an increasing exponential function, but at the same time, this is closer to this horizontal line than this exponential function. So the graph will look like this, closer to the horizontal line, but increasing, something like this. So this is the first one that we need. And then for the second one, we can use the same trick here. We can compare base 4 with base 3. And then we can see that 4, when compared to 3, it should be farther from 1 than 3. So this exponential function is an increasing one, but at the same time, this is far away from this horizontal line. So you will get it like this. Okay, the y-intercept is always 1. So this is the other one. Okay, for the decreasing exponential functions, we can do the same. So now I want to sketch these two functions on this xy plane. So you can still consider a horizontal line like this. You use this horizontal line to help you. So compared to 1/3, base half should be closer to 1 because you can consider a number line here. This is 0, this is 1, and half is here. 1/3 is here. 1/4 is here. So you can see if you compare half with 1/3, half should be closer to 1. So that means this exponential graph should be closer to this horizontal line. But at the same time, it should be a decreasing exponential function. So it will look like this, closer to this horizontal line, but decreasing. So that's the third one. And then for the fourth one, as this number is farther from 1 when it is compared to 1/3. So you will result in a decreasing exponential function, which is very far away from this horizontal line. So that's how we can sketch or how we can obtain the graph of different bases of exponential functions on the same xy plane. Finally, let's take a look at the domain and intercepts of an exponential function. To recap, an exponential function is a function in the form of a to the power x. And for this function to be an exponential function, a should be positive, but not equal to 1. And when a is greater than 1, then we will have an increasing exponential function like this. And if a is smaller than 1, then we will have a decreasing exponential function. So for the domain of this exponential function, domain means the range of values of x to make y meaningful. And in this case, the domain is all real numbers. Because we can input any value into x, and then it is still defined and we can get a meaningful value of y. For example, for a to the power 1, this is meaningful. For a to the power 0, this is still meaningful. For a to the power -1, this is still meaningful. For a to the power 0.2, a decimal number, this is always meaningful because this one is, it can be represented as fractions because this is rational and this is just the 5th root of a. So as you can see, no matter what number you input in x, you can still get a meaningful value of y. So this one, for a to the power -0.3, this is 1 over a to the power 3 over 10, which is 1 over the 10th root of a to the power 3. So we can always get a meaningful output there. For irrational indices like a to the power pi, this is irrational. For irrational indices, this is out of the scope of the secondary school curriculum, but we can take it as a fact. We know that we can still define an irrational index for a constant base. So here, we need to accept that all real numbers are qualified as the input, or the value of x in this function. So the domain is all real numbers. And for the y-intercepts, this is clear that this is always 1. And for the x-intercept, there is none. because in both cases, the graph will never cross the x-axis. So the domain of this function is all real numbers. It has a y-intercept which is always 1, and it has no x-intercept.